Hello students, next let us look into discrete time Fourier transform or DTFT. Just to give you a small idea of where we have come from the start. So if you are having a continuous time signal, the continuous time signal may either be periodic or it may be non-periodic. Periodic means which repeats itself with some period t. Okay, whereas a non-periodic signal has no period. Now the discrete time signal that we are having, the discrete time signal, that also can be periodic or non-periodic. The periodic signal in a discrete time signal will have a period of some, let's say, n naught, some n naught. Now when we are trying to take the Fourier, or when we are trying to look at the frequency analysis of continuous time signal, for the periodic signal we have what is called as the Fourier series, or sometimes written as continuous time Fourier series, CTFS. Okay, but generally it is called as Fourier series. Now the Fourier series of a periodic signal will be discrete in nature. It will be discrete in nature with values of the discrete components occurring at omega naught, where omega naught is 2 pi by this t, or the period of the continuous time signal. So you will have some value at omega naught, some value at 2 omega naught, 3 omega naught, all the way up to infinity. Similarly minus omega naught, minus 2 omega naught, and whatever is there, if you look at the magnitude of this, whatever is there in the positive axis, the same will be repeated in the negative axis. That means the magnitude will be a mirror image. Okay, now this is what basically the DTFS, the continuous time Fourier series will look like. Okay, let me just draw. So you will have only discrete values. Okay, whereas what about a non-periodic? A non-periodic one, or a non-periodic continuous time signal, to find out the frequency domain of a non-periodic signal, what we use is basically a Fourier transform, or sometimes called as continuous time Fourier transform, but generally Fourier transform. Now a Fourier transform will have a frequency plot which looks not discrete, but it is continuous. That means it will have some value which looks something like this, something. Again, its value, if you are going to take it as omega, you can also take it as f. You can find out f, or you can find out omega. Okay, here also you can find out f, or generally you go for omega. So based on Fourier transform, we get a continuous time signal. Okay, now coming to a discrete time signal, if there is a periodic signal, then we use what is called as discrete time Fourier series, something that you just previously studied, a discrete time Fourier series. And a discrete time Fourier series is discrete as well as periodic. That means whatever is the period that you are having here, suppose if it is n naught, whatever is the period from n naught, let's say that the n naught has a period of 4, then that same value will keep on repeating. That same value will keep on repeating. Okay, and what is the value here? This will be omega naught, this will be 2 omega naught, this will be 3 omega naught. Like that, its value is going to be discrete as well as it is periodic. In continuous time case, if you remember, it was discrete but it was not periodic. In case of discrete time signal, it is periodic as well as it will have a mirror image. So I cannot randomly draw like this, but it will have a mirror image on the right hand side and the left hand side. Anyway, I'm talking about the magnitude. Okay, the magnitude will have a mirror image, this side, that side. Now what we are going to study is, for the case of a non-periodic signal, what we have is basically a DTFT. What we have is basically called as DTFT, or discrete time Fourier transform, wherein the Fourier transform of a discrete time Fourier transform of a discrete time signal, it will be continuous but it will be periodic also. So I will write here, it is going to be continuous and periodic. So periodic means what? We will always draw it between minus pi to plus pi, and that value will keep on repeating itself. So here again the same thing will keep on repeating itself. Between pi and 0 pi, whatever is the value, that will keep on repeating. So you are going to take omega, then this is what you get. So this is something that you should remember. Okay, this is something that you should remember. Here if it is n naught, here omega naught is going to be equal to 2 pi by n naught. Okay, so this is 0, omega naught, twice omega naught, 3 times omega naught, like that. Okay, with this big picture in mind, let us look at the Fourier transform of the last set of signals, which is the non-periodic discrete time signals. Now one of the things is that we have to see is, why is it like this? Why is it, periodic and continuous? So I will explain that with the help of the sampling that we have studied. Now consider that in continuous time there is a signal, a continuous time signal x of t. Okay, it's a non-periodic one, whose Fourier transform, if you would try to find out, you will get a spectrum, which I will draw it as. So this is the spectrum, this is the 0 frequency, and this is some higher frequency, which is, let's say, omega max or omega m, and this will be minus omega m. Okay, this is the omega axis, and this is going to be your x of omega. Okay, now if I want to take the discrete signal of this particular continuous time signal, I have to sample it. Let me draw the sampling waveform. So this is a sampling signal which samples x of t. We will draw how the sample of x of t will look like. But if I am trying to take the Fourier transform, okay, if I am trying to take the Fourier transform of this particular signal, then what will I get? What we get is another train of impulses, which, let me draw it using the green one itself. So one impulse will be here, which will be at 0. Another impulse, let's say it is here, and another impulse here, and then it will keep on going. Okay, it will keep on going in either side. I have drawn it broad because I want to draw it properly. So if this is 0, then this is going to be equal to some omega naught, where omega naught is basically going to be with respect to this particular t. Now if I want to get a discrete time signal of x of t, I will multiply this x of t with this particular signal. And you all know that if we multiply in one domain, in the other domain we have to do convolution. Okay, so first let us do the multiplication. So now if I am going to multiply both these, the first sample is at this point, isn't it? The first sample is at this point. So that is the height of the sample that I am going to have here. At the second time, that is minus t, the sample is at this point, which is somewhat equal but a slightly on top. Okay. The third one is having a value here, so I will draw it something like this. The next sample is having a value which is here, so I will draw it like this. Then at 2t I am going to have a sample which looks something like this, which is quite large sample, so I will draw it like this. And the third one, again it comes down very drastically and its value is something going to look something like this. So this is the discrete version of x of t, which is x of n, which now instead of writing 0 t, I will write 0 1 2 3, because I'm just going to take these values. Okay, and this now I will write it as n. Similarly here it will be minus 1 minus 2, like that. Okay, now what is going to be the Fourier transform of this particular signal? See, if I want to draw the Fourier transform, generally I have to take the DTFT. Okay, generally I have to take the DTFT, but DTFT is something that you are just now going to study. Okay, so if I want to directly find out from these two, then I have to do the convolution. And convolution of anything with impulse basically means that it will have multiple copies of this one at 0, at omega naught, minus omega naught, twice omega naught, minus twice omega naught, like that. So this value is going to be repeated at each of these omega values when we do the convolution. That is something that we have already studied. So if I want to draw the plot, let me draw it. So now the spectrum at omega naught, it will look as we have drawn here, it will look something like this. It's going to be up to omega naught, omega m, sorry, and from minus omega m. Similarly, this I have to draw it at omega naught, so again I will draw here, but since there is no gap there, I will draw it only that much. Whereas here if I have to draw, again I will draw it like this and like this. Okay, and this will keep on repeating. I have done it for omega naught, I have done it for minus omega naught. Similarly, I will keep on drawing for minus 2 omega naught, plus omega naught. Like that, the value or the spectrum will keep on repeating itself. Okay, or the spectrum will keep on repeating itself for each omega naught values. Let me write the values where it will be. See, one is omega m. This is how much? This is omega naught minus omega m. Correct? Let me write that properly. So this is going to be omega naught minus omega m. This is going to be minus omega m, and this is going to be how much? This is going to be minus omega naught plus omega m. So this is going to be minus omega naught plus omega m, whereas this is going to be minus omega naught minus omega m. So like that, the spectrum will keep on repeating itself. This is going to be for the case of discrete Fourier transform x of omega. So what can you see? See, if there is an original continuous time signal, whatever its spectrum is, that same spectrum will now be repeated at omega naught minus omega naught, like that. Now, I want you to look at what is the value of omega naught. See, if you remember, omega naught here, omega naught was basically based on this t, which is 2 pi by t. Am I correct? So here if I am going to look at this particular value of omega naught, this particular value of omega naught and this particular value of omega naught, I can write it basically as minus 2 pi by t and this as 2 pi by t. Correct? As 2 pi by t. So if you would look at this particular, this much portion is again repeating, or you look at this much portion, again it is repeating. Or see how much is this length is how much? 0 to 2 pi t. See, when I came from here, I omitted t. So similarly, when I am coming here also, if I omit t, then this omega naught will basically become 2 pi, and this minus omega naught will become minus 2 pi. Correct? But what is the period? The period is only from here to here, which is 2 pi. So in a way, I can find out what is minus pi and plus pi, and I can see that the spectrum between minus pi and plus pi keeps on repeating itself. You can see this. The spectrum keeps on repeating itself. So generally what we do is we always consider, you will see in future, that we are always going to consider only the spectrum between minus pi and plus pi, because we know that whatever is here will keep on repeating in the next 2 pi, in the next 2 pi. So now remember this, we will draw the plot only for between minus pi and plus pi for the case of the DTFS of xn. Okay, the equation and all will come later, we will discuss next. But when we do the DTFT, remember that the DTFT is going to look something like this. So with this basic background, we will define what is the DTFT. The DTFT of any discrete signal x of n is basically given by the Fourier transform of x of n is capital X of omega, okay, which is given by the equation summation n is equal to minus infinity to infinity xn e raised to power minus j omega n. Okay, xn e raised to power minus j omega n. Now how we get DTFT equation like this is something that I will discuss in the very end itself. Why? Because there is a lot of mathematics involved which I don't want to now load you with. So we will see how we got this equation of DTFT, but not now, later. Okay, so this is something, this equation is something that you should remember. Remember, this is not omega naught. See, in DTFS we were doing e raised to power minus j k omega naught n. Now basically this j k omega naught has just become omega. That's the only thing. And 1 by n naught that we had here, 1 by n naught that we have here, that is vanished. So it is similar to DTFS, but basically it has got reduced to this form. How? That is something that I will discuss later. But anyway, this is the DTFT equation. Similarly, there is an inverse DTFT. The inverse DTFT of x of omega is found out by finding the Fourier inverse of x of omega, which basically gives you x of n through x of omega using the equation 1 by 2 pi summation, integration of x of omega multiplied with e raised to power j omega n d omega. And now since x of omega is repeating between minus pi and plus pi, I will write the limit only between minus pi and plus pi. Okay, so the inverse DTFT of a discrete signal is obtained by using this equation. So basically what we are having is, I will put it in a box. Basically what we are having is that using DTFT, if we are having a signal x of n, we can find out using DTFT what is the value of x of omega. Look, I am putting a square bracket in this side. Why? Because to show that it is the Fourier transform of a discrete signal. See, for a continuous time signal we had used the notation x of omega or x of f, whereas for discrete time we will write it x of within square bracket omega. Now this notation may not be followed in each and every textbook, but I will follow it in my class just because I want to have a little bit of clarity. But in certain textbooks it may not be mentioned in this way. Even x of n may not be written like this, x of n may be not written like this. In certain textbooks it may be written as x of n. That means with square, not square bracket, but simple brackets. Now using this, let us try to solve some of the numericals or some of the basic signals. For some of the basic signals, let us find out the DTFT. Let us look at the DFT of some of the basic sequence, starting with the delta n sequence. We all know that basically the equation of delta n is that delta n is equal to 1 for n is equal to 0, otherwise its value is 0, isn't it? If I'm going to draw it, I can draw it something like this. The value is at 0 it is 1, at all other times its value is 0. So to find out the Fourier transform of delta n, we use the equation which is summation n is equal to minus infinity to infinity delta n e raised to power minus j omega n. We know that since this exists only for n is equal to 0, this whole summation will be at only n is equal to 0. And if I am going to put n is equal to 0 in e raised to power minus j omega n, then it becomes 1. Delta n is equal to 1. So basically the answer is 1. Hence we can write delta n DTFT, discrete time Fourier transform, is 1. Next we will look at a shifted delta n. So if suppose we are shifting a delta n with m, it means that delta 0, we know that it is equal to 1. That means only at 0 it is equal to 1. Therefore n minus m is equal to 0 or n is equal to m. Therefore it is basically that if suppose I am having some value m, at m I am having the shifted value, at all other values the value is 0. Okay, so the first thing that I can write is delta m minus, not m, n minus m, n minus m will be equal to 1 for n is equal to m, otherwise it is 0. Therefore I am going to put it into the equation of Fourier transform of delta n minus m summation n is equal to minus infinity to infinity, and then I am going to write delta n minus m e raised to power minus j omega n, at which will exist only at n is equal to m. So if I am going to put n is equal to m, this one will become delta of 0, which we know is equal to 1, and this will be e raised to power minus j omega m. So 1 into e raised to power minus j omega m is e raised to power minus j omega m itself. Next we will look into a unit step function. A unit step function, so the third one is a unit step function. Let me, okay, unit step function u of n. We know the definition of u of n. U of n is equal to 1 only for n greater than or equal to 0, and it is 0 for n less than 0. So the Fourier transform of u of n will be summation n is equal to minus infinity to infinity, and then instead of x of n I will have u of n e raised to power minus j omega n, which, since u of n is existing only for n is equal to 0 to up, so the limit changes from, the summation changes from from 0 to infinity. U of n value is equal to 1 for this range, so multiplied with e raised to power minus j omega n. Now at this point I would like to introduce some of the summation formulas. You can write this separately, these formulas. Okay, this I have already said, but let me again repeat it. If you are having summation from some n is equal to 0 to some upper value n minus 1 of alpha raised to power n, then the formula that we will use is, if alpha is not equal to 1, then we will use this formula, and if the value of n is equal to, if the value of alpha is equal to 1, then basically this summation will turn out to be n. Okay, so that is the first formula. You can write these set of summation formulas, they are very important. If it is from 0 to infinity that you have to do for the case of an alpha whose magnitude is less than 1. See, it is very important that its magnitude has to be less than 1, because if it is not less than 1, then this answer won't suffice, it will come actually to infinity. So in all these cases, not in the first equation, but in the cases from equation number 2 to equation number 5, everywhere you will see that the value of magnitude of alpha is taken to be less than 1. Okay, so if it is from 0 to infinity alpha raised to power n, then it will be 1 by minus alpha, 1 divided by 1 minus alpha. If it is not from 0 to infinity but from some range of k to infinity, then it will be basically this. So see, you can basically understand, if I am writing some limit from n is equal to k up to infinity, I can write this as some limit from n is equal to 0 to infinity to, and minus the subtracting from it, n is equal to 0 to k minus 1. So the summation, you can see from k to infinity, the summation will be as good as finding out the summation from n to infinity and subtracting from it from n to k minus 1. If you would look here, you will see these two equations. So this is from, summation is from 0 to infinity, and this is from 0 to n minus 1. So if that is the case, then you can basically use this equation and this equation. Okay, this equation and this equation, if I am going to do, you can see that very clearly I will get this particular equation. So mainly why I am saying this is that if you remember these two, you can find out this equation. Otherwise, if you are able to by heart all the 5 equations, it will be really good. Okay, similarly, if it is n into alpha raised to power n, then the equation will be alpha divided by 1 minus alpha the whole square, and if it is n square alpha n, then it will be this particular equation. You can write it down separately, you can pause the video, you can write these 5 equations separately and use it according to your problem. So right now we are going to use this particular equation because this is what we have just now seen here. So here you can see e raised to power minus j omega n. If I am trying to take the magnitude of e raised to power minus j omega n, its value is going to be equal to 1. So I can basically write this equation, consider this equation as, so I will write using summation n is equal to 0 to infinity n alpha raised to power n will be equal to 1 by 1 minus alpha You might be thinking that, sir, I am writing here 1. No problem. You know, you can directly use this formula. So using this, what will I get? I will get that the Fourier transform of u of n is equal to 1 divided by 1 minus e raised to power minus j omega n. Not n, e raised to power minus j omega. The n is gone. The n is basically gone. So e raised to power minus j omega n. So from this I can directly say, therefore u of n, the DTFT is going to be equal to 1 divided by 1 minus e raised to power minus j omega. Okay. The next one is a very important sequence, which we will generally write it as a raised to power n u of n. Why I am writing this is because if you would look for any exponentially rising sequence, or if you are going to look for a, so this is not exponentially rising, okay. Suppose if you are looking for an exponentially rising sequence, which is rising like this, exponentially it is rising, or you are looking for a linear sequence, okay. If you are looking for a linear sequence, in that case also, everywhere you can use this particular equation. Just change the value of a. You will either have an exponentially rising one, or you will having an exponentially decaying signal, okay. But all of this will be only in the right hand side of the time axis, because it is all multiplied with u raised to u of n, okay. So using this equation, we can write for the exponential sequence. Many sequences can happen here, so we will try to generally find out what is the DFT of this particular equation or sequence. So the Fourier transform of a raised to power n u of n is going to be given by summation n is equal to minus infinity to infinity. Then the signal is a raised to power n u of n e raised to power minus j omega n, which, since u of n is existing only from 0 to infinity, we will rewrite the summation limit as n is equal to 0 to infinity a raised to power n, u of n will be 1, then e raised to power minus j omega n, which we can very conveniently write it as n is equal to 0 to infinity. Now a raised to power n and e raised to power minus j omega n, it's similar to a raised to power n into b raised to power n. We know that if we have such a case, then we can basically write a into b the whole raised to power n, correct. So using that same principle, I will join these two together and I will write a into e raised to power minus j omega the whole raised to power n. And then if I am using the formula, the formula is summation n is equal to 0 to infinity alpha raised to power n. We have seen this summation formula. You might be thinking, why am I writing this formula again and again? Because once you keep on writing it again and again, it will register in your memory. Okay, anyway, see, what is important here is what is the magnitude of a e raised to power minus j omega. It is equal to a. Why? Because this is the magnitude portion and this is the phase angle portion, correct. So the magnitude is going to be a. So a should never be less than, sorry, it should not be greater than 1. So one of the conditions here that we should remember is that a should be greater than, the magnitude of a should be not greater than, it should be less than 1. Less than 1. Can be less than or equal to 1 also. Less than 1, not equal to, less than 1. Okay, so that thing you have to take care that a should always be less than 1. So based on that, now I will write the equation to be, therefore the Fourier transform of a raised to power u of n is going to be equal to 1 divided by 1 minus a e raised to power minus j omega. Correct? Therefore, I can say that a raised to power n u of n, the DTFT is going to be 1 divided by 1 minus a e raised to power minus j omega. The next sequence is also important. So this was the fourth. The next sequence is also important. It is minus of a raised to power n u of minus n minus 1. Now here also it's basically a sequence which can be an exponentially rising sequence or an exponential decaying sequence, with the only condition that it is going to be a left-handed sequence. It's not going to be a right-handed sequence. That means it is going to exist only for negative value of n. Only for the negative values of n we will have this particular function, either increasing or decreasing, whatever be the case. Okay, so what you should remember is, for this was for a right-handed sequence, and the next is for a left-handed sequence. Let us find out the Fourier transform of this. Now the Fourier transform equation we all know of minus a raised to power n u of minus n minus 1 will be given by the equation n is equal to minus infinity to infinity minus a raised to power n u of minus n minus 1 e raised to power minus j omega n. And since this is existing only for minus infinity to minus 1, I can rewrite this particular summation limit as this is equal to summation n is equal to minus infinity to minus 1 minus a raised to power n u of minus n minus 1 is equal to 1 e raised to power minus j omega n. And now here, if I am going to say put n is equal to minus n, so if I am going to put n is equal to minus n, then the limit basically changes from n is equal to infinity to 1, because n is equal to minus n. And similarly here it is going to be minus a raised to power minus n, and this becomes e raised to power j omega n. Why? Because I have put n is equal to minus n, which can be rearranged as summation n is equal to 1 to infinity minus of a raised to power minus 1. Okay, this minus I will take it outside. So this minus I will take it outside, and I will write this as minus of this a raised to power minus 1 e raised to power j omega, and then commonly I will write it as n. Okay, now we know that, let me use the equation using summation n is equal to 0 to infinity alpha raised to power n is equal to 1 by 1 minus alpha. Then from here, if I am going to put n is equal to 0, if n is equal to 0, then this alpha raised to power n is equal to alpha raised to power 0, which is equal to 1. Okay, so if I am going to use that, therefore summation n is equal to 1 to infinity of alpha can be written as alpha raised to power 0. Okay, I can write it as summation n is equal to 0 to infinity raised to power alpha raised to power n minus at n is equal to 0, that is alpha 0. Okay, which I can then write it as, therefore summation n is equal to 1 to infinity alpha raised to power n can then be written as 1 divided by 1 minus alpha raised to 0 is 1. So this becomes 1 minus alpha divided by 1 minus alpha, which comes out to be alpha divided by 1 minus alpha. Okay, so using that I can write the Fourier transform as, so now I'm going to use this particular equation. So basically I will get alpha is now a raised to power minus 1 e raised to power j omega divided by 1 minus a raised to power minus 1 e raised to power j omega, and in front of that there is a minus value. We should not forget that, this one. So using that also I will write a minus here, where if I am going to write a raised to power minus alpha minus 1 as 1 divided by a e raised to power j omega divided by 1 minus 1 by a e raised to power j omega, such that I can take a the other side and all, then basically I will get this is equal to 1 divided by 1 minus a e raised to power minus j omega. You can solve this on your own. From here to here it is a very simple step. Okay, so you can find out that. So therefore a raised to power n u of minus n minus 1, the discrete time Fourier transform is going to be 1 divided by 1 minus a e raised to power minus j omega. Now what is interesting here is that this value and this value, both of them, you can have a look, both of them are actually one and the same. So whether it's a left-handed sequence or a right-handed sequence, the DTFT of that is going to be one and the same. Okay, with this we will finish today. We will take the next portions in the next class. Thank you.